Out there, in the frozen depths of our solar system, beyond the orbit of Neptune, hides a world so strange it rewrote the rules of astronomy. Meet Eris, the dwarf planet shrouded in mystery, a cosmic rebel that forced scientists to rethink what it even means to be a planet. Discovered in 2005, this distant speck of ice and rock didn't just join the solar system's family, it turned it upside down. Its sheer size and gravitational pull sparked a debate so fierce that Pluto, once the ninth planet, was stripped of its title. But Eris didn't stop there. This enigmatic world holds secrets far stranger than its role in Pluto's downfall. From its bizarre, almost unnatural orbit to the unexplained glint of its surface, Eris behaves like no other object we've found. And that's just the beginning. What if I told you Eris might be hiding something beneath its icy shell, or that its surface reflects light in ways that defy explanation? This isn't just another frozen rock drifting in the void. It's a puzzle wrapped in layers of cosmic intrigue. Scientists have spent nearly 2 decades studying Eris, and with every answer, new questions emerge. Why is its orbit so wildly tilted compared to the rest of the solar system? What causes its surface to shine like a distant beacon? And could there be forces at work we haven't even begun to understand? The more we learn, the more Eris feels less like a dwarf planet and more like a messenger from the shadows of space, whispering clues about the universe's best-kept secrets. Today, we're diving deep into the 25 most baffling mysteries of Eris, each one a thread in a tapestry of cosmic wonder. From its explosive discovery to the mind-bending anomalies that still leave astronomers scratching their heads, we'll explore why this tiny world holds such big questions. Some of these enigmas might even challenge what we think we know about the outer solar system. So buckle up, because by the time we're done, you'll never look at that distant speck of light the same way again. The story of Eris isn't just about a planet that wasn't. It's about the mysteries that still are, and they're waiting for us to uncover them. Eris doesn't just drift through the solar system, it practically dances on the edge of chaos. Unlike most objects in the Kuiper Belt, which orbit the Sun in relatively flat, predictable paths, Eris follows a wild, erratic trajectory. Its orbit isn't just elliptical, it's steeply tilted, angling almost 44 degrees off the plane where planets like Earth and Mars circle. To put that in perspective, imagine a marble rolling around a dinner plate, then suddenly veering off to spin sideways across the table. That's the kind of cosmic rebellion we're dealing with here. So what flung Eris onto this bizarre path? One leading theory suggests a gravitational kick from Neptune billions of years ago, a common fate for objects in the outer solar system. But here's the twist: Eris' orbit is too extreme to be explained by Neptune's influence alone. Some astronomers speculate it might have been yanked out of place by an unseen, larger object, perhaps a rogue planet that once lurked in the solar system's early days before being ejected into interstellar space. Others wonder if Eris didn't just get knocked around by a massive collision, sending it careening into its current oddball orbit. The real mystery: no matter how many simulations scientists run, they can't quite recreate Eris' exact celestial choreography. It's as if the dwarf planet holds a grudge against predictability. Even more puzzling is how stable its orbit has remained over time. Most objects with such extreme tilts eventually get tugged back into alignment by the Sun's gravity, but not Eris. It stubbornly maintains its off-kilter path, almost as if some unseen force is holding it in place. Could there be another player in this cosmic game, something we haven't detected yet? Or does Eris itself hold clues about a chaotic chapter in our solar system's history that we've yet to uncover? Every time astronomers think they've cracked the case, Eris throws another curveball. Its orbit isn't just a fluke, it's a fingerprint of forces we're only beginning to understand. And until we solve this puzzle, Eris will keep defying the rules, reminding us that the outer solar system is far stranger than we ever imagined. Eris's extreme orbital tilt isn't just unusual, it's downright defiant when compared to its cosmic neighbors. Take Pluto, for instance, which orbits the Sun at a relatively modest 17-degree angle. Even Haumea, another Kuiper Belt oddball with a speedy, football-like spin, keeps its orbit within 28 degrees of the solar system's main plane. But Eris, it scoffs at convention, soaring 44 degrees above and below the ecliptic like a celestial pendulum gone rogue. This kind of inclination isn't just rare for dwarf planets, it's virtually unheard of among sizable solar system objects, making Eris more like an interstellar visitor than a native-born member of our cosmic neighborhood. The question gnawing at astronomers is whether Eris's tilt is a cosmic accident or a clue to forgotten chaos. Some simulations suggest our early solar system may have hosted a fifth giant planet, a gravitational bully that could have hurled Eris askew before being ejected into deep space. Imagine a game of planetary pinball where Neptune and this hypothetical rogue planet battered objects like Eris into bizarre orbits during the solar system's violent youth. There's tantalizing evidence for this theory in the peculiar orbits of other distant objects like Sedna, which also follow extreme, unexplained paths. Could these cosmic misfits be survivors of an ancient gravitational upheaval, their odd trajectories serving as breadcrumbs to a lost chapter of our solar system's history? But here's where it gets stranger. Eris's current orbit is almost too perfect, not just tilted, but locked in a precise gravitational resonance with Neptune. For every 2 trips Neptune makes around the Sun, Eris completes exactly one, maintaining this rhythm despite its wild inclination. It's as if some celestial choreography keeps this dwarf planet in step even as it dances to its own tune. This delicate balance defies expectations. Most objects knocked into extreme tilts eventually have their orbits circularized by the Sun's gravity over billions of years. Yet Eris persists, its path frozen in cosmic amber. Some researchers speculate its orbit might be actively maintained by unseen forces, perhaps the cumulative tug of countless smaller Kuiper Belt objects, or even subtle influences from the Milky Way's gravity itself. The more we study Eris's peculiar trajectory, the more it resembles a time capsule from the solar system's most chaotic era. Its orbit may encode secrets about epic collisions, lost planets, or gravitational disturbances we've yet to imagine. While other dwarf planets like Makemake and Quaoar follow relatively sedate paths, Eris stands apart, a celestial maverick whose tilted path challenges our understanding of how solar systems evolve. Every new calculation reveals another layer of mystery, proving that in the outer darkness where Eris dwells, the rules of planetary motion might be written in ink we're still learning to read. If there's one feature of Eris that immediately catches the eye both literally and figuratively, it's the way this distant world gleams like a cosmic disco ball. Shrouded in perpetual twilight nearly 68 times farther from the Sun than Earth, Eris shouldn't be this luminous, yet it reflects a staggering 96% of the sunlight that hits it, making it brighter than fresh snow on Earth and outshining every known object in the outer solar system except Saturn's moon Enceladus. This isn't just unusual, it's borderline unnatural. Most Kuiper Belt objects, even relatively large ones like Pluto or Makemake, reflect only 30 to 70% of incoming light. So why does Eris act like a celestial mirror? The leading suspect is methane ice, but not the ordinary kind we find on Pluto. Eris's surface appears coated in an ultra-reflective form of methane that's been chemically altered by billions of years of cosmic radiation. Imagine leaving a block of dry ice in a deep freezer for eons, where solar wind and high-energy particles slowly transform its texture into something akin to frosted glass. This irradiated methane, called a tholin, could explain the extreme reflectivity except for one glaring inconsistency. Lab experiments show that even the most processed methane ice shouldn't bounce back quite this much light. Some researchers speculate Eris might be expelling fresh methane through cryovolcanoes, constantly resurfacing itself with pristine ice before radiation can darken it. Others propose exotic ices like nitrogen or carbon monoxide could be mixed in, creating a hyper-reflective cocktail unlike anything we've seen elsewhere. Then there's the temperature problem. At a bone-chilling -400 degrees Fahrenheit, Eris is so cold that most gases should freeze solid and stay put. Yet spectroscopic readings reveal puzzling seasonal changes in its brightness, as if something on the surface is actively shifting over time. Could Eris have a tenuous atmosphere that periodically sublimates and refreezes like Pluto but on a much smaller scale? Or does its elliptical orbit, which takes it from 38 to 97 astronomical units from the Sun, trigger dramatic freeze-thaw cycles that refresh its gleaming crust? Stranger still, Hubble telescope observations show subtle dark patches marring Eris's otherwise uniform shine features that rotate in and out of view, but don't match any known surface patterns on similar worlds. The most tantalizing possibility involves crystalline ice. Under certain conditions, water ice molecules can arrange themselves into a near-perfect lattice structure, becoming extraordinarily reflective. Europa and Enceladus exhibit this phenomenon due to constant geologic activity grinding and reheating their icy shells. But Eris, with no obvious heat source or tidal forces to churn its surface, shouldn't behave this way unless there's internal energy we haven't accounted for. Could residual heat from its formation, or even radioactive decay in a rocky core, be maintaining liquid reservoirs beneath the ice that occasionally breach the surface? The New Horizons probe's flyby of Pluto revealed sprawling glaciers and nitrogen geysers where no one expected activity, so why couldn't Eris, smaller but more massive, harbor similar surprises? Every attempted explanation for Eris's brilliance unravels new questions. Its shininess isn't just a curiosity, it's a beacon pointing toward processes we're only beginning to comprehend in the solar system's frozen hinterlands. Whether the answer lies in exotic chemistry, hidden geology, or something entirely unforeseen, one thing is clear: Eris refuses to be just another icy rock in the dark. It demands we rethink what's possible in the outer solar system, and reminds us that even in the coldest reaches of space, there are still mysteries glowing bright enough to catch our eye. Just when astronomers thought they had Eris figured out, its brightness started playing tricks on them. Over years of observations, something baffling emerged: the dwarf planet's reflectivity isn't constant. It fluctuates as if Eris has cosmic mood swings. These shifts don't follow predictable seasonal patterns like those on Mars or Earth. Instead, they appear erratic, sometimes brightening or dimming over spans of mere months. For an object with a 558-year orbit, that's like a glacier changing color between breakfast and lunch. Theories abound to explain this flickering enigma. One possibility involves Eris's tenuous atmosphere, a whisper-thin layer of vaporized ices like nitrogen or methane that might sporadically erupt from its surface. When sunlight intensifies during its closest approach to the Sun, these frozen gases could sublimate into temporary hazes, scattering light differently across Eris's reflective crust. As the dwarf planet retreats into the outer solar system's deep freeze, these hazes might collapse back into frost, restoring its mirror-like shine. It's a compelling idea, except spectral analysis hasn't detected the telltale absorption lines such an atmosphere should leave. Another twist comes from Eris's rotation. Unlike Pluto, which shows distinct dark and bright regions as it spins, Eris's light variations don't neatly sync with its 25.9-hour day. Some patches seem to brighten independently, as if hidden geysers are spraying fresh ice across localized areas. This wouldn't be entirely unprecedented. Neptune's moon Triton has nitrogen geysers that resurface its terrain, but Eris lacks the tidal heating that powers Triton's eruptions. Unless there's an unknown heat source buried beneath Eris's shell, these spotty brightening events make little sense. then there's the wild card, cosmic impacts. The Kuiper Belt is a shooting gallery of icy debris, and a collision could blast away darkened surface layers to expose brighter material underneath. But the odds of frequent enough impacts to explain Eris's flickering are astronomically low. Even stranger, Hubble observations show no new craters corresponding to these brightness surges. It's as if Eris is healing itself, renewing its gleaming facade without leaving scars. The most tantalizing explanation lies in Eris's chemistry. Recent studies suggest its methane ice might undergo phase transitions, shifting between crystalline and amorphous structures as temperatures fluctuate. These molecular rearrangements could dramatically alter how light reflects off its surface. On Saturn's moon Titan, similar processes cause lakes of liquid hydrocarbons to vanish and reappear over time. But Titan has thick atmospheric pressure to facilitate these changes. Eris operates in near-vacuum conditions where such transformations should be impossible. Yet the data doesn't lie. Something on Eris is actively reworking its surface in ways that defy textbook physics. Every attempted explanation runs into the same problem. Eris shouldn't be this dynamic. At its distance from the Sun, temperatures barely budge, and solar radiation is a faint whisper. Most objects this far out are effectively frozen in time, their surfaces unchanged for eons. Yet Eris behaves like a living world, pulsing, shifting, and refusing to sit still. Whether through hidden geology, exotic chemistry, or forces we haven't yet imagined, this distant dwarf planet continues to challenge our understanding of what's possible in the solar system's darkest corners. One thing's certain: when we finally send a probe to Eris, the textbooks will need rewriting. Eris threw the astronomical community into chaos from the moment its size was first estimated. Initial measurements in 2005 suggested a diameter surpassing Pluto's, making it the largest object discovered in the solar system since Neptune's moon Triton in 1846. Overnight, this icy upstart became the poster child for the planet debate, forcing the International Astronomical Union to redefine what qualified as a planet. But here's where things get messy. Later observations revealed Eris might actually be slightly smaller than Pluto, yet somehow more massive. How could scientists get something as fundamental as size so wrong? The answer lies in the extreme challenges of measuring a faint speck nearly 10 billion miles away. The discrepancy stems from two key factors: reflectivity and distance. Early size estimates relied on Eris's brightness and assumed an average reflectivity for Kuiper Belt objects. But when astronomers realized its surface was almost perfectly mirror-like, far more reflective than Pluto's, they recalculated. A shinier surface means Eris could be smaller while appearing just as bright, like how a compact disco ball outshines a larger matte sphere. Then came the Hubble Space Telescope's direct measurements in 2007, which suggested a diameter around 1,446 miles, roughly 20 miles narrower than Pluto's. Yet when Eris passed in front of a star in 2010, a rare event called an occultation, Earth-based telescopes captured data implying an even more compact size. But the plot thickens with Eris's mass. Despite potentially being smaller in diameter, it outweighs Pluto by nearly 30%. This means Eris is astonishingly dense for an icy world, packing more rock into its core than expected. Some models suggest its interior could be 85% rocky material, far higher than Pluto's 50-50 ice rock split, raising questions about how such different compositions emerged in similarly sized bodies. The controversy doesn't end there. Recent thermal emission studies using the ALMA telescope present yet another twist. Eris's surface temperature doesn't match predictions based on its reflectivity. Colder than expected, the readings imply either unknown surface properties or internal heat leaking through cracks in its icy shell. This thermal anomaly could mean earlier size estimates are still off by tens of miles. Why does this matter? Because every decimal place in Eris's dimensions reshapes our understanding of the solar system's outskirts. If Eris is smaller but heavier than Pluto, it challenges formation models that predict uniform compositions for objects in the Kuiper Belt. Its density suggests violent collisions or exotic accretion processes we've never observed, and the ongoing measurement disputes highlight a humbling truth. Even with cutting-edge technology, pinning down the basics of distant worlds remains fraught with uncertainty. Until a spacecraft visits Eris, something no mission currently plans, this dwarf planet's true stature will keep astronomers debating, proving that some cosmic mysteries refuse to be measured from afar. The battle to measure Eris became a high-stakes game of cosmic guesswork between two of astronomy's greatest tools, the Hubble Space Telescope orbiting Earth and New Horizons, our first visitor to Pluto. Hubble's 2007 observations suggested Eris was a hair smaller than Pluto, around 1,446 miles across. But when New Horizons flew past Pluto in 2015, it delivered a shock. Pluto was slightly larger than anyone thought, stretching 1,473 miles in diameter. Suddenly, Hubble's estimate for Eris seemed off by nearly 30 miles. The discrepancy traces back to how these instruments see distant worlds. Hubble relies on optical measurements, essentially taking photographs and calculating size based on pixel counts. At Eris's distance, a single pixel spans dozens of miles, making fine details impossible to resolve. New Horizons, by contrast, flew close enough to Pluto to measure its silhouette directly against the stars during occultations, achieving precision down to a few hundred feet. This raised an uncomfortable question. If Hubble's Pluto size was wrong, could its Eris data be equally flawed? Then came the curveball. In 2022, astronomers combined Hubble's visible light data with thermal infrared readings from the Atacama Large Millimeter Array in Chile. The results suggested Eris might be even more compact, perhaps as small as 1,430 miles across. Why the chaos? It all comes down to albedo, a world's reflectivity, and how it tricks our instruments. Hubble's size calculations assume a uniformly bright surface, but if Eris has dark patches hidden from view, its true diameter could be larger than the thermal data suggests. Alternatively, if its icy shell is even shinier than we've measured, the opposite might be true. New Horizons added another wrinkle. When it examined Pluto's moons, it found their surfaces were far darker than predicted, meaning similar shadows could lurk on Eris, skewing old estimates. The mission also revealed Pluto's atmosphere bends light in unexpected ways, a phenomenon called refraction that could have distorted earlier Earth-based measurements of both worlds. Without a dedicated flyby, Eris's atmosphere, if it even has one, remains a wild card in the size debate. The stakes here aren't just academic. A few dozen miles might seem trivial, but they dramatically alter our understanding of how objects form in the Kuiper Belt. If Eris is significantly denser than Pluto despite being smaller, it implies radically different origins. Perhaps a cataclysmic collision stripped away its outer layers, leaving a rocky core draped in thin ice. Or maybe Eris formed in a hotter, more volatile region of the early solar system, acquiring a unique composition before being flung outward. For now, the answer lies frustratingly out of reach. Even the James Webb Space Telescope struggles with this puzzle. Its infrared eyes excel at studying composition, not geometry, the only way to settle the debate. A mission to Eris itself, something no space agency has yet greenlit. Until then, this dwarf planet's true size remains a tantalizing enigma, reminding us that in astronomy, sometimes the simplest questions are the hardest to answer. Eris isn't alone in its cosmic dance. It's partnered with a moon so peculiar, it deepens the dwarf planet's mysteries rather than solving them. Meet Dysnomia, a dim, irregularly shaped satellite named after the Greek spirit of lawlessness, a fitting title for an object that refuses to follow expectations. Discovered just months after Eris itself in 2005, this moon orbits at a slanted angle, tracing a wide, elliptical path that defies the neat circular orbits of most planetary companions. Even stranger, Dysnomia's surface appears darker than charcoal, a stark contrast to Eris's mirror-like shine, raising questions about whether these two objects were ever truly siblings or strangers forced together by cosmic chance. The most puzzling aspect of Dysnomia isn't just its appearance, it's how it moves. While most moons orbit along their parent planet's equatorial plane, Dysnomia's path is tilted by roughly 78 degrees, making its motion more like a sputtering top than a graceful circle. This extreme inclination suggests one of two possibilities. Either Dysnomia was violently captured by Eris's gravity after a close encounter, or it's the shattered remnant of an ancient collision that shaped Eris itself. The capture theory would explain the moon's odd tilt, but there's a problem: Dysnomia's composition. What little we can discern from its faint light hints at water ice similar to Eris's surface. Captured objects usually differ dramatically from their hosts, like Neptune's moon Triton, which is likely a stolen Kuiper Belt refugee with a distinct makeup. This leaves the collision scenario a cataclysmic impact that might have birthed both Eris's moon and its peculiar orbit. Imagine a protoplanet smashing into early Eris with enough force to vaporize part of its icy mantle, ejecting debris that later coalesced into Dysnomia. Such an event could have also knocked Eris into its current off-kilter solar orbit, solving two mysteries at once. But here's the catch: Dysnomia is far smaller than typical collision-born moons. Our own moon was created when a Mars-sized object struck Earth, leaving a satellite nearly a quarter the size of its parent. Dysnomia, by contrast, is a mere 150 miles across, at just 1% of Eris's bulk. For an impact to create such a lopsided pairing, the physics would require an impossibly precise, low-energy collision. Then there's Dysnomia's darkness. Spectroscopic studies reveal almost no reflective ice, a trait shared with few known Kuiper Belt objects except the most ancient, radiation-battered relics. If Dysnomia formed alongside Eris, why hasn't it retained any bright surface material? Some researchers speculate it might be coated in organic compounds cooked up by eons of cosmic rays, while others propose its surface is littered with rubble from countless micro-impacts, creating a porous, light-absorbing texture. The most radical theory suggests Dysnomia could be a captured comet nucleus, a primordial iceberg stripped of volatiles, leaving behind a crust as dark as dried tar. What makes Dysnomia truly enigmatic is its silence. Most moons betray their origins through subtle compositional clues or orbital dynamics, but this one guards its secrets fiercely. Even its name, meaning anarchy, feels prophetic, a celestial rebel that refuses to fit neat scientific narratives. Until we send a probe to study this odd couple up close, Dysnomia will remain a cosmic riddle wrapped in shadow, reminding us that even the smallest objects can hold the keys to the solar system's most profound mysteries. The spectral fingerprints of Dysnomia tell a story starkly at odds with its dazzling parent world. While Eris beams sunlight back with mirror-like efficiency, its moon absorbs light like a cosmic sponge, reflecting less than 5% of incident radiation, making it one of the darkest natural objects ever measured in the solar system. This isn't just a superficial difference. Spectroscopic analysis reveals Dysnomia's surface lacks the telltale methane ice signatures that dominate Eris's spectrum. Instead, faint absorption lines hint at complex organic compounds called tholins, the same dark, reddish gunk found on Pluto's moon Charon and Saturn's distant satellite Phoebe. But here's the catch. Tholins typically form when methane gets bombarded by radiation over billions of years. If Dysnomia was born from the same material as Eris, where did all its methane go? One possibility is that Dysnomia started life as a fragment of Eris's interior rather than its surface. Imagine a colossal impact blasting through Eris's icy crust and hurling material from its rocky core into orbit. Over time, this debris could have coalesced into a moon with little surface ice to begin with. Supporting this theory are subtle spectral features suggesting silicates, minerals common in asteroid belts but rare among Kuiper Belt objects. Yet even this explanation falters under scrutiny. Thermal emission data shows Dysnomia's surface is too cold to be bare rock, implying some kind of insulating layer. Some researchers propose it might be blanketed by a porous, comet-like crust of carbon-rich dust, a material that could explain both its darkness and its puzzling thermal properties. The plot thickens when comparing Dysnomia to other collision-borne moons. Earth's moon shows isotopic signatures nearly identical to our planet, proof of their shared origin. Pluto's moon Charon, despite being half rock, still shares key chemical markers with its parent, but preliminary studies of Dysnomia's light curve suggest its density might be significantly higher than Eris's, an impossible mismatch if they formed from the same debris cloud. This raises the radical possibility that Dysnomia isn't a native moon at all, but a captured asteroid or comet nucleus that wandered too close to Eris's gravity. The Kuiper Belt does contain scattered dark objects like Dysnomia, including the mysterious ultra-red populations that may originate from even farther out in the Oort cloud. Yet the capture theory has its own glaring hole: orbital dynamics. Dysnomia's path around Eris is too circular for a typical captured object, which usually follow elongated, erratic orbits like Neptune's moon Triton. Computer simulations show that gravitational interactions would have either flung a captured Dysnomia away or circularized its orbit over billions of years. But Eris's diminutive size lacks the gravitational muscle to accomplish this feat quickly. Unless some third body once complicated their dance, the moon's present orbit remains inexplicable. Perhaps the most tantalizing clue lies in what we don't see. Dysnomia's spectrum shows no evidence of water ice normally ubiquitous in the outer solar system, yet Eris itself likely contains vast subsurface oceans. If Dysnomia was born from Eris, why is it so dehydrated? One controversial hypothesis suggests intense heat from the hypothetical impact that created it might have vaporized all volatile ices, leaving behind only refractory materials. Alternatively, Dysnomia could be what astronomers call a monolith, a dense shard of primordial material that survived the solar system's violent infancy untouched by melting or differentiation. Every layer of analysis deepens the enigma. Dysnomia's darkness, composition, and orbit paint a portrait of an object that shouldn't exist in its current form, a celestial paradox clinging to Eris as if taunting us to unravel their shared past. Whether it's a battered survivor of cosmic violence, an interstellar refugee, or something even stranger, this moon stands as a stubborn reminder that the outer solar system still holds puzzles no textbook can yet solve. Until a spacecraft visits this odd couple, Dysnomia will remain a shadowy cipher, a lawless moon living up to its name. Pluto wears its atmosphere like a fleeting scarf, a tenuous shroud of nitrogen, methane, and carbon monoxide that swells when the dwarf planet nears the sun and collapses as it retreats. Yet Eris, its cosmic cousin, stands naked in the void. Despite sharing comparable sizes, icy compositions, and even surface temperatures, Eris shows no detectable atmosphere, an absence so glaring it forces astronomers to rethink how these distant worlds interact with the frigid darkness around them. The puzzle begins with basic physics. At Eris's bone-chilling -400 degrees Fahrenheit, gases like nitrogen and methane should freeze solid, blanketing the surface in ice. On Pluto, solar heat, feeble as it is, periodically sublimates these ices into a temporary atmosphere. But Eris's orbit, which swings from 38 to 97 times Earth's distance from the Sun, creates even more extreme temperature swings. During its closest approach, sunlight is still 3,000 times dimmer than on Earth, barely enough to warm a snowflake. Yet something prevents even this meager energy from loosening molecules from Eris's grasp. One clue lies in Eris's mirror-like surface. That 96% reflectivity means almost all incoming sunlight bounces away, leaving little heat to vaporize ices. Pluto, by contrast, absorbs more solar energy due to its darker patches, fueling atmospheric production. But this can't be the full story. Even if Eris's surface stayed frozen, impacts from micrometeorites or cosmic rays should knock molecules loose over time, creating at least a wispy exosphere. The fact that we detect nothing suggests something far stranger is at work, an active mechanism scrubbing gases from Eris's vicinity, the leading theory. Eris's higher density and stronger gravity might be trapping gases in an unexpected way, while Pluto's low gravity lets its atmosphere slowly escape into space. Eris's extra mass could pull sublimated gases back down before they reach high altitude, like a cosmic vacuum cleaner reversing its own leaks. Alternatively, Eris's surface chemistry might bind gases into stable compounds. On Pluto, sunlight breaks methane apart, forming dark hydrocarbon tholins that litter the terrain. If Eris's methane transforms into heavier, less volatile molecules under its extreme cold, these compounds could act like molecular glue, preventing gases from ever taking flight. Then there's the time factor. Eris takes 558 years to orbit the Sun, nearly twice as long as Pluto. Its atmospheric cycles, if any, might operate on scales too prolonged for our brief observations to catch. Imagine a world where air forms only for a few decades every millennium, a fleeting breath in the cosmic deep freeze. Compounding the mystery, Eris's axial tilt could hide atmospheric activity from Earth-based telescopes. If gases only vent from poles angled away from our line of sight, we'd never know they existed. The most tantalizing possibility involves internal sequestration. Pluto's atmosphere is partly replenished by geysers and cryovolcanoes tapping into subsurface reservoirs. If Eris's higher rock content locks away volatiles in its crust, or if its thicker ice shell prevents outgassing, its gases might remain imprisoned underground. New Horizons revealed Pluto's heart-shaped glacier actively recycling nitrogen. Eris, lacking such obvious geology, could be a static ice vault where nothing stirs. Or perhaps its gases escape not upward but downward, seeping into hidden subterranean oceans, forever lost to the vacuum above. Every explanation circles back to the same realization: Eris isn't just Pluto without an atmosphere. It's a fundamentally different kind of world, governed by rules we've yet to fully decipher. Whether through gravity, chemistry, or sheer cosmic circumstance, this dwarf planet has become a laboratory for extremes, showing us how fragile the balance is between air and ice in the solar system's farthest reaches. Until we peer closer, Eris's missing atmosphere will remain one of its most haunting silences. What if Eris does have an atmosphere, but one so fleeting our telescopes keep missing it? The idea isn't as far-fetched as it sounds. Seasonal atmospheres exist across the solar system, from the frosty plumes of Saturn's moon Enceladus to the intermittent methane hazes on Pluto. These ethereal envelopes form when sunlight vaporizes surface ices, only to freeze back solid as temperatures drop. Eris's extreme orbit, wildly elliptical and tilted, creates perfect conditions for such ephemeral activity. During its rare close approaches to the Sun, surface temperatures might rise just enough to sublimate pockets of nitrogen or methane ice, creating a whisper-thin atmospheric layer lasting mere decades before the deep freeze reclaims it. Detecting these vanishing acts is like trying to photograph a snowflake melting in midair. Current telescopes lack the sensitivity to spot ultra-thin atmospheres unless they're chemically distinct, like Pluto's nitrogen-rich veil. Eris's potential air, if dominated by methane or carbon monoxide, might blend into the background of cosmic radiation. Even more confounding, Eris's mirror-like surface could be masking atmospheric clues. When Hubble and other observatories analyzed the dwarf planet's reflected light, that 96% reflectivity washes out subtle spectral fingerprints that gases would normally leave. It's the equivalent of searching for candle smoke in front of a floodlight. Timing is another hurdle. Eris's seasonal cycles operate on a scale humans haven't observed directly. Its last perihelion, the closest point to the Sun, occurred around 1896, decades before we could study it. By the time telescopes became powerful enough, Eris was already retreating into the outer darkness. The next chance won't come until 2038, leaving us stuck in a cosmic waiting game. Even then, Eris's axial tilt means any atmospheric activity might concentrate near poles hidden from Earth's view, like a shy child peeking around a corner. Some researchers propose creative workarounds. One team suggested looking for atmospheric glints, momentary flashes when sunlight catches gas molecules at just the right angle during Eris's slow rotation. Another method involves monitoring how Eris dims background stars during occultations. A sudden dimming before the main event could hint at atmospheric refraction. So far, these techniques have come up empty, but not for lack of trying. In 2022, astronomers used Chile's ALMA array to hunt for carbon monoxide emissions, a telltale sign of atmospheric activity. The result, radio silence. The most compelling evidence for a ghostly atmosphere might come from an unexpected source, Eris's brightness variations. Those unexplained flickers could trace to ephemeral frosts forming and dissipating as hidden gases migrate across its surface. Pluto exhibits similar behavior. Its heart-shaped glacier pumps nitrogen into the atmosphere seasonally, creating bright frost patches elsewhere on the planet. If Eris has even 1,000th of Pluto's atmospheric pressure, similar processes could be at work on a microscopic scale. Perhaps the greatest irony is that Eris's atmosphere might not be missing at all, just hiding in plain sight. When New Horizons flew past Pluto, it discovered haze layers 10 times thicker than Earth-based estimates. Eris could be cloaked in an equally misunderstood veil, one that doesn't behave like any model predicts. Until a dedicated probe makes the long journey to this frozen outpost, we're left piecing together clues from 10 billion miles away, watching, waiting, and wondering if Eris breathes in secrets we've yet to perceive. Even with its immense distance blurring most details, Eris's surface teases us with geological whispers we can't quite decipher. Through the faint pixelated glimpses from Hubble and ground-based telescopes, astronomers have spotted irregular patches of brightness, not the smooth, uniform shine expected from a world coated in pristine methane ice, but jagged transitions suggesting dramatic terrain. Some regions appear suspiciously smooth, like frozen seas of nitrogen reminiscent of Pluto's Sputnik planitia. Others show abrupt dimming, hinting at sprawling impact basins or fractures slicing through the icy crust. But the most tantalizing anomalies are the occasional dome-like bulges features that, if confirmed, could point to cryovolcanic activity where slushy mixtures of water, ammonia, or methane once oozed onto the surface like cosmic toothpaste. What makes these formations so perplexing is their sheer improbability. Cryovolcanoes need internal heat to operate, yet Eris's tiny size, just 2/3 the diameter of Pluto, should have lost any primordial warmth eons ago. Even radioactive decay in its rocky core seems insufficient to power such activity, unless, of course, Eris harbors secrets beneath its shell. One radical theory suggests tidal forces from Dysnomia, its moon, might flex Eris's interior, though the moon's small size and distant orbit make this effect negligible by most calculations. Alternatively, Eris could retain heat through an antifreeze-like mixture of ammonia and water beneath the surface, lowering the freezing point enough to maintain pockets of slushy brine. This same chemistry fuels the geysers of Enceladus, but Saturn's moon benefits from intense gravitational kneading by its giant host planet, a luxury Eris lacks in the isolated Kuiper Belt. Then there are the Dark maculae are mysterious blotches first noted in 2015 that rotate in and out of view. Unlike Pluto's dark highlands, which are tinted by Tholen deposits, these patches show no clear spectral signature. Some researchers propose they might be impact scars where collisions vaporized surface ices, exposing darker bedrock underneath. Yet Eris's high reflectivity suggests its icy shell is remarkably thick, making bedrock exposures unlikely. Another possibility: these could be sinkholes formed as subsurface liquids drained away, leaving collapsed pits akin to Earth's karst landscapes, except here, the liquids would be volatile ices sublimating into voids below. The most controversial feature appears near Eris's southern pole, a faint, elongated depression spanning an estimated 300 miles. Too large to be a typical crater, some speculate it could be a relic impact basin from the collision that birthed Dysnomia. But its edges appear softened, not sharp like younger basins on Pluto or Charon. If erosion is at work, what force could be smoothing terrain at temperatures where ice behaves like bedrock? Wind is impossible without an atmosphere, and tectonic activity seems improbable without measurable internal heat. One fringe hypothesis invokes solid-state convection, where ice slowly flows over millions of years due to subtle temperature gradients, a process seen on Neptune's moon Triton, but requiring warmer conditions than Eris should experience. Every blurry pixel deepens the intrigue. Without close-up observations, these surface features remain Rorschach tests open to interpretation but resisting confirmation. Are we seeing cryovolcanic plains, ancient scars from forgotten impacts, or geological processes we've yet to imagine? The answer might rewrite not just Eris's story, but our understanding of how small, icy worlds evolve in the solar system's silent outskirts. For now, these enigmatic formations stand as ghostly landmarks on a world that refuses to be known from afar. Among Eris's shimmering expanse of reflective ice lies a feature so out of place it seems almost unreal, a shadowy blotch astronomers refer to simply as the dark spot. First glimpsed in Hubble images as a smudge of inconsistent albedo, this anomaly refuses to conform to expectations. Unlike Pluto's dark highlands, which span vast regions, Eris's spot is compact yet stark, like a fingerprint on freshly polished glass. Initial theories proposed it might be an impact crater, except the surrounding terrain lacks the raised rims or radiating fractures typical of cosmic collisions. Without the resolution to see details, scientists are left debating whether this is geology, chemistry, or something even stranger. The spot's composition presents the first headache. If it were a crater exposing darker subsurface material, spectroscopic analysis should detect water ice or silicates. Instead, the region absorbs light uniformly across wavelengths, a trait more consistent with complex organic molecules than simple bedrock. Some researchers point to tholins, the same reddish-brown gunk found on Pluto's moon Charon, created when methane cooks under cosmic radiation. But Eris's surface is too cold and reflective for tholin production at scale, leaving the spot's origin in limbo. Others suggest it could be a localized deposit of carbon-rich dust, perhaps delivered by a comet strike. The problem: no known comet impact leaves such a neat, isolated stain without surrounding debris. Then there's the spot's bizarre stability. Over a decade of observations, it hasn't faded or shifted as Eris rotates, behavior unheard of for surface features on volatile, rich worlds. Pluto's dark patches migrate as nitrogen ice sublimates and refreezes. Even Mars's polar caps evolve with the seasons, yet Eris's spot remains fixed, almost painted onto the terrain. One radical explanation proposes it might be a cold trap, a topographic depression where heavier gases like ethane or propane could pool and freeze, creating a permanent dark film. On Saturn's moon Titan, similar processes form hydrocarbon lakes, but Titan has both an atmosphere and internal heat to drive the chemistry. Eris possesses neither, making the theory a stretch. The most tantalizing and contentious idea involves cryovolcanic tar. On Earth, petroleum seeps create asphalt pits like California's La Brea tar pits. If Eris once harbored subsurface organic sludge, perhaps a fissure vented this material onto the surface, where it hardened into a black crust. The concept isn't entirely far-fetched. The Cassini probe found complex hydrocarbons on Saturn's icy moons. But for Eris to host such chemistry, it would require both an improbable concentration of organics and a heat source to liquefy them, conditions nobody predicted for a world this small and remote. Skeptics argue the dark spot might not even be a real feature. At Eris's distance, Hubble's pixels span dozens of miles, making it possible the anomaly is an artifact, a chance alignment of noise in the data. New Horizons' encounter with Pluto revealed how wildly Earth-based interpretations can miss the mark. Entire mountains in pre-flyby images turned out to be optical illusions. Until we send a probe to Eris, the dark spot will remain in scientific purgatory, too intriguing to dismiss, too ambiguous to explain. Whether it's a cosmic ink blot, a window into alien chemistry, or a trick of the light, this enigmatic stain reminds us that even in the age of precision astronomy, some mysteries refuse to surrender to pixels alone. Most celestial objects in the Kuiper Belt spin like frantic tops. Pluto whirls on its axis every 6.5 days. Haumea completes a dizzying rotation in under 4 hours, and even distant Makemake pirouettes in about 8 hours. Then there's Eris, moving with the lethargy of a cosmic sloth. Current estimates suggest this dwarf planet takes around 25 hours to complete a single turn, nearly matching Earth's 24-hour day in a region where speedy spins are the norm. This sluggish rotation isn't just odd, it's a glaring anomaly that hints at hidden chapters in Eris's violent past. The mystery begins with basic physics. When objects form from collapsing clouds of gas and dust, conservation of angular momentum dictates they should spin faster as they shrink, like an ice skater pulling in their arms. This explains why most Kuiper Belt objects rotate quickly. They've preserved the frenetic energy of their birth. Eris's leisurely twirl defies this expectation, suggesting something or someone hit the brakes. The prime suspect, a colossal impact early in the solar system's history, powerful enough to dramatically slow Eris's spin. Consider the math. If an object roughly half Eris's size struck it at an angle, the transfer of momentum could have acted like a cosmic hand grabbing a merry-go-round, bleeding off rotational energy. This scenario gains credibility when we examine Dysnomia, Eris's moon. Most collisional satellites like Earth's moon or Pluto's Charon orbit in sync with their parent's equatorial plane. Dysnomia's wildly inclined path suggests the hypothetical impactor came in at a steep angle, delivering a glancing blow that didn't just create a moon but also robbed Eris of its spin. But here's where the puzzle deepens. Even after accounting for a moon-forming collision, Eris's rotation should have sped up over time as its orbit brought it closer to the Sun. Gravitational interactions during these perihelion passages typically torque Kuiper Belt objects into faster spins, yet Eris remains stubbornly slow. Some theorists propose its internal structure acts like an invisible damper. If Eris contains a subsurface ocean, even a slushy, ammonia-rich one, tidal forces could have gradually sapped its rotational energy. Much like Jupiter's gravity breaks the spin of its ocean-bearing moon Europa. Another possibility involves Eris's peculiar composition. With a density suggesting an unusually rocky core for its size, this dwarf planet might have a radically different moment of inertia than its icy neighbors. Imagine two spheres of identical size, one hollow, one solid. The solid sphere resists changes to its spin far more effectively. If Eris's mass is concentrated toward its center, it would naturally rotate more slowly unless acted upon by extreme external forces. The implications ripple outward. Eris's languid rotation affects everything from potential atmospheric circulation to the distribution of surface ices. On rapidly spinning worlds like Haumea, centrifugal force flings volatile ices toward the equator, creating distinct brightness bands. Eris's gentle turn allows ices to settle more uniformly, possibly contributing to its bizarrely reflective surface. And if internal tides are indeed slowing its spin, that process would generate heat, potentially explaining how this frigid world maintains enough energy to flicker mysteriously in our telescopes. Every theory circles back to the same realization. Eris's rotation isn't just a curious statistic. It's a fossil record of violence and transformation, a speedometer frozen in time that tells us this dwarf planet didn't simply form and drift quietly into the darkness. Something dramatic happened here, something that left Eris spinning not with the reckless abandon of its neighbors, but with the measured pace of a world that's endured cosmic upheaval and emerged forever changed. Most moons and planets engage in a gravitational tug-of-war, gradually sapping each other's spin until one becomes tidally locked, forever showing the same face to its partner, like Earth's moon. Dysnomia, Eris's small but persistent companion, seems like an unlikely candidate for such cosmic choreography. At barely 150 miles across, its gravitational grip should be too feeble to noticeably slow Eris's rotation. Yet here's the puzzle. Eris spins at almost the exact same leisurely pace as Mercury, a planet thoroughly braked by the Sun's immense gravity. Could Dysnomia, despite its modest size, be responsible for this anomaly? The math paints a complicated picture. Tidal locking depends on three factors: distance, mass, and time. Our moon needed 1 billion years to lock Earth's rotation relative to its own orbit, and it's both massive and relatively close. Dysnomia, by contrast, orbits Eris at a distance of 24,000 miles, 10 times farther out than the moon is from Earth. At that range, its gravitational influence should be whisper-thin. Yet simulations suggest that if Dysnomia formed from a colossal impact, much like Earth's moon, it might have started much closer to Eris, where tidal forces were stronger. Over billions of years, gravitational interactions could have gradually pushed the moon outward while simultaneously slowing Eris's spin, creating the odd couple we see today. There's a catch, though. For this scenario to work, Eris would need some internal flexibility, a subsurface ocean or slushy mantle that could absorb and dissipate rotational energy as heat. On icy worlds like Jupiter's Europa, such oceans allow tidal forces to reshape the crust and alter spin rates. But Eris's orbit lacks the massive gas giants that keep Europa's interior churning. Without an external source of gravitational kneading, how could it maintain enough internal heat for tidal braking? One controversial hypothesis suggests radioactive decay in Eris's unusually large rocky core might provide just enough warmth to keep its icy shell slightly pliable, allowing Dysnomia's weak tugs to add up over eons. The wildcard is Dysnomia's bizarre orbit. Tidal locking typically requires a moon to orbit above its planet's equator, yet Dysnomia circles at a steep 78-degree tilt. This extreme angle means its gravitational pull yanks Eris's rotation axis as much as it slows the spin, creating a wobble that defies standard models. Some astronomers argue this chaotic interaction might actually prevent full tidal locking, leaving Eris in a strange halfway state where its spin slows but never stabilizes. Others propose that Dysnomia's odd path could be evidence of a past upheaval, perhaps a close encounter with another Kuiper Belt object that jarred the moon into its current inclined orbit, scrambling any progress toward synchronization. Unraveling this mystery could rewrite our understanding of small celestial partnerships. Most tidally locked systems involve either massive planets with close orbiting moons or tiny objects with negligible rotation. Eris and Dysnomia sit in a gray zone too distant to conform to textbook examples, yet too peculiar to ignore. Until we measure Eris's exact libration, the slight wobble that would betray tidal forces at work, their relationship remains a cosmic guessing game. One day, a spacecraft might catch Eris mid-wobble, revealing whether Dysnomia's subtle tug is truly the architect of its slow spin, or if some deeper, unseen force is at play in this frozen corner of the solar system. At first glance, Eris should be a frozen wasteland locked in perpetual stasis, a world so distant and cold that thermodynamics would seem to pause entirely. Yet infrared telescopes reveal a shocking truth. This dwarf planet runs hotter than expected in some regions, with temperature variations that shouldn't exist on a uniformly cooling Kuiper Belt object. The discrepancies are subtle, just a few degrees above predictions, but in the icy depths of the outer solar system, even minor thermal anomalies are like smoke signals hinting at hidden fires. The first clues emerged from Chile's Atacama Large Millimeter Array, which detected unexpected heat signatures near Eris's equator. Normally, objects this far from the sun should radiate heat evenly, like a forgotten ice cube left in the back of a freezer. Instead, Eris shows patches where subsurface warmth appears to bleed through its gleaming crust. The most baffling aspect, these warm spots don't align with any visible surface features. If cryovolcanism or impacts were responsible, we'd expect craters or fissures, yet Hubble sees only unbroken expanses of reflective ice where the heat lingers. One theory points to Eris's unusually high density. With a rock-rich core making up nearly 80% of its mass, radioactive decay from elements like potassium-40 and thorium-232 could provide just enough energy to create localized hotspots. On larger worlds like Earth, this heat dissipates through tectonic activity, but Eris's thick icy shell might act like a thermos, trapping decay-generated warmth in isolated pockets. The math almost works, except that even the most generous estimates of Eris's radiogenic heating fall short of explaining the observed temperature spikes by at least a factor of 3. Another possibility involves Eris's albedo playing tricks on thermodynamics. That 96% reflectivity means most sunlight bounces right off, but the tiny fraction absorbed could be distributed unevenly due to microscopic variations in surface texture. Picture sunlight hitting a field of fresh snow. While most reflects away, slight melting around dust particles creates dimpled surfaces that absorb more heat over time. On Eris, a similar process might occur with methane ice grains, creating self-reinforcing warm zones where initial absorption triggers subtle sublimation, further darkening the surface and amplifying the effect. Then there's the wild card, phase transitions in exotic ices. At Eris's cryogenic temperatures, methane and nitrogen can form crystalline structures with strange thermal properties. When these ices shift between molecular arrangements, they release or absorb latent heat, a process seen on Neptune's moon Triton, where nitrogen geysers erupt from sun-warmed plains. If pockets of Eris's surface ice are undergoing similar transitions, they could generate localized temperature surges without any external energy input. The implications ripple far beyond academic curiosity. Thermal anomalies on a world this small and distant suggest that heat, and therefore geologic activity, might persist in places we once considered dead and frozen. If Eris, why not Sedna or Gong, or any of the other dwarf planets drifting in the Kuiper Belt's shadowy recesses? These tiny temperature deviations could rewrite our understanding of how celestial bodies age, proving that even in the deepest freeze, cosmic embers continue to glow. The notion that Eris might harbor an internal heat source challenges everything we know about small, distant worlds. In the frozen reaches of the Kuiper Belt, objects this size should have cooled off billions of years ago, their primordial heat long since radiated into space. Yet those puzzling thermal anomalies, subtle but persistent, suggest something is keeping Eris's icy veins from running completely cold, the prime suspect. Radioactive decay deep within its unusually dense core, Eris's composition holds the first clue. While most icy bodies in the outer solar system are roughly half rock and half ice, Eris's staggering density implies its rocky core might make up 80% or more of its mass. That's a treasure trove of radioactive elements like uranium, thorium, and potassium isotopes that naturally decay over time, releasing heat as they do. On Earth, this process drives plate tectonics and volcanic activity. In Eris's smaller frame, even modest radiogenic heating could create localized warm zones beneath the ice. But there's a catch. Models show the heat output from radioactive decay alone shouldn't be enough to explain the temperature spikes we're seeing. Unless Eris's core is enriched with rare, extra-potent isotopes, something we've never observed in similar worlds, this theory only solves part of the puzzle. Tidal heating presents another tantalizing possibility. We know gravitational flexing can warm moons like Europa and Enceladus as they orbit gas giants, but Eris lacks such a massive dance partner. Its moon Dysnomia is too small and distant to generate significant tidal forces, or so we thought. Recent simulations reveal a subtle twist. Eris's slow rotation and Dysnomia's inclined orbit might create a resonant tug of war, flexing the dwarf planet's interior in ways we haven't accounted for. Imagine gently wiggling a rubber ball over millennia. The internal friction generates trace heat. It's a faint effect, but over billions of years, even this trickle of energy could accumulate into observable anomalies. Then there's the wild card, serpentinization. On Earth, this chemical reaction between water and certain rocks generates heat as it forms new minerals. If Eris's rocky core contains olivine or other reactive silicates common in asteroids, any residual liquid water percolating through fractures could trigger similar exothermic reactions. The catch: this process typically requires liquid water contacting rock, which demands both geological activity and internal warmth to begin with, a classic chicken or egg dilemma. The frustrating truth is that every explanation demands conditions just outside the bounds of what we consider plausible for Kuiper Belt objects. Radioactive decay requires improbably enriched cores. Tidal heating needs finely tuned orbital resonances. Even serpentinization presumes geological dynamics we've never observed in worlds this small. Yet the thermal signatures persist, whispering of processes we've yet to imagine. Perhaps Eris's heat isn't from one source but many, a cocktail of radiogenic decay, tidal friction, and phase transitions in exotic ices, each contributing just enough to tip the scales. Until a probe arrives to take Eris's temperature up close, these anomalies will remain cosmic riddles. They challenge our assumptions about how small, distant worlds evolve, and remind us that even in the darkest corners of the solar system, cold isn't always absolute. Sometimes it's just waiting for us to uncover its exceptions. Naming a celestial object is rarely just an exercise in mythology. It's a statement, a reflection of how we interpret cosmic discoveries through human narratives. When the team behind Eris's discovery proposed its name in 2005, they didn't just reach for a random Greek deity. They chose Eris, the goddess of discord, a figure synonymous with strife and upheaval. At first glance, it might seem like an inside joke among astronomers, a nod to the dwarf planet's role in Pluto's controversial demotion. But the symbolism runs deeper, echoing centuries of scientific revolutions where new discoveries forced us to rewrite the rules. The parallels are almost poetic. In myth, Eris famously sparked the Trojan War by tossing a golden apple inscribed "to the fairest" among rival goddesses. Her real-world counterpart ignited its own battle, one that played out in academic journals and International Astronomical Union meetings. By revealing a world larger than Pluto, Eris forced astronomers to confront an uncomfortable truth. Our solar system might be teeming with Pluto-like objects, and calling them all planets would render the term meaningless. The resulting debate divided the scientific community, with some arguing for Pluto's grandfathered status and others demanding a stricter definition. Eris, true to its namesake, became the apple of discord in this cosmic drama. Critics accused the name of being unnecessarily provocative, a jab at traditionalists who resisted reclassifying Pluto. But the discoverers, led by Mike Brown, insisted the choice was about honesty. Science, like mythology, thrives on disruption. Copernicus displaced Earth from the center of the universe, Galileo's telescope shattered crystalline spheres, and now Eris challenged our sentimental attachment to a 9-planet solar system. The name wasn't just a celebration of chaos, it honored the messy, often contentious process of discovery itself. Not everyone embraced the symbolism. Some in the astronomical community pushed for alternate names like Persephone or Layla, options that lacked Eris's confrontational edge. Even the public weighed in, with Pluto loyalists accusing the name of being mean-spirited. Yet history suggests Eris was inevitable. Astronomy has a long tradition of letting discoveries name themselves through their impact. Uranus, discovered in 1781, was initially called Georgium Sidus after King George III, but the scientific community rejected the political flattery in favor of mythological consistency. Eris's name followed the same unspoken rule: let the cosmos dictate the narrative. Beyond the controversy, the choice reveals something profound about how science grapples with paradigm shifts. Eris isn't just a dwarf planet, it's a cultural artifact, a reminder that even in the pristine realm of celestial mechanics, human emotions and rivalries play out. The goddess's legacy lingers every time a textbook calls Pluto a dwarf planet, or when a new generation of stargazers learns a solar system model that no longer includes their childhood's 9th planet. Like its mythological counterpart, Eris didn't just disrupt, it transformed, leaving an indelible mark on how we map the heavens. And perhaps that's the most fitting tribute of all, a name that doesn't just describe an object, but the seismic shift it represents. The ripples from Eris's discovery didn't just stay confined to academic circles. It spilled into popular culture, reshaping how the public viewed the solar system. Suddenly, the tidy model many grew up with 9 planets neatly orbiting the Sun was thrown into chaos. Classroom posters needed updating, textbooks required revisions, and trivia games had to rewrite their answer keys. For the first time in generations, people who'd never given astronomy a second thought found themselves debating planetary definitions over dinner tables. The controversy wasn't just scientific, it was emotional. Pluto, a celestial underdog beloved for its small size and quirky orbit, had been demoted, and Eris, the newcomer, became the inadvertent villain of the story. This cultural shift went deeper than nostalgia. Eris's discovery forced a broader conversation about how we categorize the cosmos. Before 2005, the word planet felt fixed, almost sacred, a title bestowed by tradition rather than strict criteria. But Eris, along with other Kuiper Belt objects like Makemake and Haumea, exposed the flaws in that system. The public witnessed science in real time, not as a set of unchanging facts, but as a process of questioning, revising, and sometimes appending what we thought we knew. For some, it was unsettling. For others, it was exhilarating. The debate even spilled into unlikely places. Late-night comedy sketches riffed on Pluto's identity crisis, while articles in mainstream magazines explained the nuances of hydrostatic equilibrium to curious readers. The name Eris itself became a cultural shorthand for disruption. In tech circles, startups adopted the moniker to signal they were challenging industry norms. Online forums buzzed with comparisons between the dwarf planet and other agents of change. From disruptive innovations to political revolutions, the goddess of discord had found her modern avatar, not just in mythology but in the collective imagination. Even those who couldn't point to Eris in a star chart understood its symbolic weight. Progress often comes with friction, and sometimes you need a little chaos to reveal deeper truths. Yet beneath the noise, something subtler took root, a renewed public engagement with planetary science. Museums reported spikes in attendance at astronomy exhibits. Planetarium shows added segments on the Kuiper Belt. The very debate Eris sparked became a gateway for educators to discuss how scientific classifications evolve. Kids who might have tuned out a lecture on celestial mechanics suddenly leaned in when the topic turned to Pluto's fate. In an unexpected twist, Eris's legacy wasn't just about redefining planets, it was about reminding people that science is alive, adaptable, and unafraid to correct its own course. The dwarf planet's influence even reached the arts. Poets penned verses about cosmic identity, while indie bands named albums after its mythological namesake. A playwright staged a tragicomedy where Pluto and Eris argued their cases before a celestial court. These creative responses underscored something profound. Eris had transcended its physical form to become a metaphor. It stood for the tension between tradition and progress, between sentiment and rigor, a mirror held up to our own struggles with change. Looking back, it's clear Eris did more than expand the solar system's map. It reshaped how we think about discovery itself. The controversy it ignited wasn't a flaw in the process, it was the process. Every paradigm shift from Copernicus to Darwin has faced resistance. Eris simply gave the 21st century a front-row seat to that timeless dance, and in doing so, it left an indelible mark not just on astronomy, but on the way we grapple with new ideas both in the stars and here on Earth. When astronomers first trained their spectroscopes on Eris, they expected to see the familiar fingerprint of methane ice that dominates other Kuiper Belt giants like Pluto and Makemake. Instead, the light bouncing back from this distant world told a far stranger story, one written in wavelengths no one predicted. Hidden within Eris's gleaming reflection were spectral lines suggesting nitrogen frozen so pure it resembled Antarctic lake ice, alongside tantalizing hints of complex organic molecules that shouldn't survive at these temperatures. This wasn't just unusual chemistry, it was a cosmic recipe that defied every expectation for how objects in the solar system's freezer should age. The nitrogen signature proved especially baffling. On Pluto, nitrogen exists in a dynamic cycle, sublimating into atmosphere, freezing onto poles, and mixing with other ices to form pinkish tholins. But Eris's nitrogen appears eerily isolated, forming crystalline structures so pristine they scatter light with uncanny efficiency. Laboratory experiments show nitrogen ice this pure requires formation temperatures below -400 degrees Fahrenheit colder than most of the Kuiper Belt. Even more puzzling, nitrogen should gradually darken under cosmic radiation, yet Eris's surface remains blindingly bright. Some researchers speculate its nitrogen might be sequestered beneath a protective methane layer, only exposed during rare surface disruptions. Others propose exotic deposition processes, perhaps geysers spewing liquid nitrogen that flash freezes into ultra-reflective snow. Then there are the organics. Faint absorption lines around 3.4 micrometers suggest the presence of carbon chains, molecules like ethane or ethylene that typically form when methane gets zapped by solar radiation. The twist: at Eris's distance, sunlight is too weak to drive such chemistry. One radical theory suggests charged particles from the solar wind, funneled by Eris's weak magnetic field, could be irradiating select surface patches. Another possibility involves internal processes. If Eris harbors even trace subsurface water, radiolyses could break it into hydrogen and oxygen, with the oxygen then reacting with methane to create unexpected compounds. The most tantalizing clues come from spectral shoulders, subtle bumps in the data that don't match any known ices. Some researchers argue these could signal irradiated organic sludge similar to Titan's dunes, while others detect parallels with comet dust samples returned by the Stardust mission. If confirmed, it would mean Eris's surface hosts a cocktail of primordial material that somehow avoided being cooked into simpler molecules over billions of years. This would make it less a time capsule from the solar system's birth and more like a cosmic refrigerator preserving ingredients older than the planets themselves. Every attempted explanation runs into the same paradox. Eris's spectrum suggests both extreme antiquity, pristine ices untouched by heating, and surprising dynamism with complex molecules that require energy to form. It's as if someone took Pluto's chemistry, erased all the intermediate steps, and left only the starting and ending materials. Until we can sample this distant world directly, its spectral oddities will remain a cipher, a reminder that even in the age of Webb and Hubble, some cosmic puzzles refuse to reveal their secrets through light alone. The debate over what truly coats Eris's surface reads like a cosmic whodunit, with methane and nitrogen as the prime suspects, each leaving contradictory clues across the dwarf planet's icy expanse. On one side, the methane camp points to spectral signatures unmistakably matching irradiated methane ice, the kind that forms when solar ultraviolet light breaks down simple molecules into complex organic gunk over billions of years. This fits Eris's blinding reflectivity. Pure methane ice, especially when cooked by radiation into a hardened glaze, can become extraordinarily shiny. Yet there's a snag. Methane alone can't explain the bizarre thermal properties or those fleeting spectral hints of nitrogen lurking in the data. Enter the nitrogen theorists. They argue that Eris's extreme brightness better aligns with nitrogen, frost, the same material that blankets Pluto's glaciers in a mirror-like sheen. Nitrogen ice, when freshly condensed, reflects up to 98% of sunlight, eerily close to Eris's measurements. But nitrogen comes with its own paradoxes. At Eris's distance, nitrogen should be as immobile as concrete, yet the dwarf planet's surface shows subtle variations that suggest some degree of seasonal migration. Pluto's nitrogen dances across its surface thanks to trace atmospheric pressure, but Eris lacks even that wispy veil to transport molecules. Unless nitrogen is somehow erupting from below, a cryovolcanic feat requiring internal heat no one can confirm, its presence remains as puzzling as its absence. The plot thickens with hybrid theories. Some researchers propose a layered cocktail, a thin veneer of methane masking deeper deposits of nitrogen like frosting on a cosmic cake. This could explain why Eris's spectrum changes slightly over time. Methane-rich patches might sublimate under rare bursts of solar warmth, exposing nitrogen beneath. Others suggest a stranger mix, ethane ices or even acetylene snow, compounds forged when methane interacts with cosmic rays. These exotic blends could account for both the reflectivity and the odd thermal readings, but they'd require chemical processes we've never observed in such a cold, static environment. Then there's the wild card crystalline water ice. Ordinarily, water ice in the Kuiper Belt is about as reflective as dirty sidewalk snow, but under certain conditions, it can rearrange into a highly reflective hexagonal structure. If Eris's water ice were somehow kept unnaturally pure, perhaps by an insulating layer of other ices, it might contribute to the overall shine. Yet no current model explains how water ice could stay clean and crystalline for billions of years without darkening from radiation. The stakes here are higher than mere chemistry. If Eris runs on methane, it's a relic of the solar system's primordial carbon reservoir. If nitrogen dominates, it challenges our understanding of how volatile compounds migrate to the outer solar system. And if the answer is something entirely novel that could rewrite the playbook for how icy worlds evolve in darkness, every pixel of data deepens the intrigue, painting Eris not just as a distant dwarf planet, but as a Rosetta Stone for decoding the frozen alchemy of the Kuiper Belt. Until a spacecraft finally peers past its gleaming veil, this icy enigma will keep its secrets one reflecting surface at a time. When Eris first blipped onto astronomers' radar in 2005, it didn't just shake up Pluto's status, it triggered an identity crisis for our entire solar system. Initial observations suggested this icy world beyond Neptune was significantly larger than Pluto, instantly raising a provocative question. If Pluto was the 9th planet, didn't Eris have an even stronger claim to being the 10th? The Discovery team's early measurements sent shockwaves through the International Astronomical Union, forcing scientists to confront a glaring inconsistency they'd ignored for decades. For all the childhood mnemonics about "my very educated mother just served us 9 pizzas," no formal definition actually existed for what made a planet a planet. The debate erupted like a cosmic supernova. Traditionalists argued size alone should dictate planetary status, pointing out that Eris and Pluto both cleared their orbital neighborhoods over time, a key criterion for planethood. But the more astronomers looked, the messier things became. The same survey that found Eris also revealed other sizable Kuiper Belt objects like Makemake and Haumea. If all these worlds became planets, our solar system might soon balloon to dozens or even hundreds of planetary members. Opponents of expansion invoked the asteroid belt precedent, when Ceres, discovered in 1801, was initially classified as a planet until similar objects appeared nearby. History seemed to be repeating itself in the frozen outskirts of our cosmic neighborhood. Into this fray stepped the International Astronomical Union, convening a contentious 2006 meeting where astronomers narrowly voted to establish 3 planetary criteria: orbiting the Sun, achieving hydrostatic equilibrium, a spherical shape from self-gravity, and clearing one's orbital path. Pluto and Eris, while spherical, shared their orbital zones with other icy bodies, failing the third test. Overnight, the solar system shrank to 8 planets, with Eris and Pluto relegated to the new dwarf planet category, a classification that remains controversial to this day. Mike Brown, Eris's discoverer, famously tweeted, "Pluto is dead," only to later grapple with his own role in rewriting celestial taxonomy. What made Eris the tipping point wasn't just its size, it was timing. Earlier discoveries like Quaoar and Sedna had already hinted at Pluto's non-uniqueness, but Eris's preliminary measurements suggested it outmatched Pluto in bulk. Astronomers suddenly faced the prospect of endless planet additions with every powerful new telescope. The public backlash, however, exposed how deeply planetary science intertwines with human emotion. Children wrote letters protesting Pluto's demotion. State legislatures in New Mexico and Illinois passed symbolic resolutions defending its status. Eris, cast as the disruptive newcomer, became a cultural lightning rod for debates about how we categorize the cosmos. The irony, later measurements revealed Eris might actually be slightly smaller than Pluto, just more massive due to its rock-rich composition. But by then, the damage was done. The IAU's decision had already reshaped textbooks worldwide, proving science isn't just about facts but the frameworks we build to contain them. Eris's true legacy isn't as a 10th planet or a Pluto killer, but as the celestial catalyst that forced us to define what we mean by planet at all, a definition that remains delightfully unsettled, waiting for the next discovery to challenge it once more. The International Astronomical Union's 2006 decision to demote Pluto and classify Eris as a dwarf planet was meant to settle the debate, but in reality, it sparked a controversy that still simmers today. While the IAU's 3-part planet definition brought order to textbooks, a vocal faction of planetary scientists argues the criteria were arbitrary, rushed, and fundamentally flawed. Their dissent isn't just bureaucratic nitpicking, it challenges whether we've misunderstood planetary diversity altogether. Take the clearing your orbit requirement, the rule that sank Pluto and Eris. Critics point out that even mighty Jupiter shares its path with Trojan asteroids, while Earth's orbit crosses thousands of near-Earth objects. If orbital dominance is the benchmark, why don't these gas giants and rocky worlds fail the test? The line between cleared and uncleared orbits starts to blur under scrutiny, revealing what some call a double standard favoring the 8 classical planets. Alan Stern, principal investigator of NASA's New Horizons mission, has been particularly outspoken, arguing the IAU's definition was crafted by astronomers who study stars. not planetary bodies, leading to a disconnect with how geologists and planetary scientists view these worlds. Then there's the question of hydrostatic equilibrium, the idea that planets must be round from self-gravity. Eris and Pluto easily meet this criterion, as do moons like Ganymede and Titan, which are larger than Mercury. If roundness defines planethood, why exclude massive spherical worlds simply because they orbit other planets? The inconsistency fuels arguments that the IU's definition is more about sentiment than science, preserving tradition rather than reflecting celestial reality. Some researchers propose a geophysical definition: any non-stellar body massive enough to become round regardless of location. Under this model, Eris wouldn't just be a planet, it would join a roster of over 100 similarly qualified worlds across the solar system. The stakes are higher than semantics. Classification shapes exploration priorities and funding. NASA's Dawn mission, for example, targeted Ceres and Vesta precisely because they were seen as protoplanets, a term with more prestige than asteroids. Similarly, calling Eris a dwarf planet might subconsciously relegate it to second-tier status, despite its potential to teach us about solar system evolution. As Mike Brown, Eris's discoverer, once conceded, the public doesn't care about dwarf planets, they care about planets. Perhaps the most compelling case for reclassification comes from exoplanet research. When we study worlds around other stars, we don't apply the IU's orbital clearance rule. We call any round, non-fusor a planet. This cosmic inconsistency leaves us in the absurd position of having planets light years away that would be dwarfs in our own solar system. As astronomer Kirby Runyon notes, nature doesn't care where something orbits. A planet is a planet, whether it's around the sun or another star. The backlash isn't unanimous, of course. Many astronomers support the IU's framework, arguing that without strict criteria, the term planet becomes meaningless. They compare it to biological taxonomy. Just as not every arthropod is a crustacean, not every round celestial body needs to be a planet. But even they admit the current system is imperfect. The divide underscores a deeper truth. Eris didn't just expose flaws in Pluto's planethood. It revealed how hard it is to categorize nature's complexity into human-made boxes. What's next? Some advocate for a tiered system, perhaps classical planets versus dwarf planets, to honor both tradition and science. Others suggest scrapping the IU's definition entirely. One thing's certain, as missions like New Horizons reveal active geology on Pluto and potential oceans inside Eris, the pressure to revisit these labels will only grow. The debate isn't just about Eris's status. It's about whether our solar system's map should reflect nostalgia or the breathtaking diversity of worlds we're still discovering. Eris's gravitational dance with Neptune is one of those cosmic coincidences that feels almost too perfect to be random. For every 2 trips Neptune makes around the Sun, Eris completes exactly one, a precise 2-to-1 resonance that keeps these distant worlds locked in an intricate celestial rhythm. On paper, this synchronization suggests they've been gravitationally whispering to each other across billions of miles and billions of years. But proving that connection is like trying to hear a conversation through a hurricane, because out in the Kuiper Belt, nothing is ever that simple. The first puzzle lies in Eris's extreme orbital tilt. Most resonant objects like Pluto orbit close to the same flat plane as Neptune, making their gravitational handshakes obvious. Eris, by contrast, cartwheels around the Sun at a 44-degree angle, like a metronome swinging sideways. For it to maintain resonance from such a skewed position defies conventional models. Computer simulations show Neptune's gravity should have broken this synchronization long ago, unless some unseen factor is reinforcing it. Some theorists speculate Eris might be shepherded by the collective tug of smaller Kuiper Belt objects, their combined influence acting like an invisible conductor keeping the beat. Others wonder if Eris's resonance isn't with Neptune at all, but with a larger, undiscovered object further out, a ghost planet whose gravity stitches this strange pattern into place. Then there's the timing problem. Orbital resonances typically form early in a solar system's life, when planets and debris are still jostling for position. But Eris's current orbit is wildly unstable over long timescales, suggesting it arrived in this resonant groove relatively recently. One provocative theory posits that Eris was once a closer neighbor to Neptune, perhaps even a Trojan companion like those that lead and trail Jupiter. A passing star or rogue planet could have yanked it outward, leaving it teetering in this improbable harmony. Supporting this idea are Eris's spectral similarities to smaller Neptunian Trojans, icy worlds that might have once shared its orbital zip code before chaos scattered them across the solar system. The most tantalizing clue comes from the broader population of detached Kuiper Belt objects, bodies like Sedna and 2467 ATZ, which orbit so far from Neptune that its influence should be negligible. Yet many share subtle orbital patterns hinting at coordinated movement. Eris might be part of this larger celestial choreography, its resonance with Neptune just one thread in a web of gravitational relationships we're only beginning to trace. The Gaia spacecraft star mapping data recently revealed faint perturbations in Neptune's orbit that could be fingerprints of these distant interactions, if only we could untangle their meaning. What makes Eris's resonance so maddening and so fascinating is that it exists at the edge of detectability. Each new observation adds another piece to the puzzle, but the full picture remains frustratingly out of focus. Are we seeing the last echoes of the solar system's violent youth, or evidence of forces we've yet to imagine? For now, Eris keeps its secrets ticking away in the darkness like a clock with hands we can't quite read. Eris isn't the only rebel drifting through the solar system's frozen outskirts. It's part of a growing family of misfits whose orbits defy conventional wisdom. Among them, Sedna stands out as Eris's enigmatic counterpart. Discovered in 2003, this reddish dwarf planet takes 11,400 years to complete a single orbit, swinging so far from the Sun that at its most distant, our star would appear as little more than a bright speck in its sky. Like Eris, Sedna follows an extreme path, highly elliptical and tilted, but with one key difference. Its orbit stretches so far out that Neptune's gravity barely touches it. This makes Sedna a detached object, floating in a cosmic no-man's land where theories struggle to explain its origin. Yet when astronomers plot the paths of Eris, Sedna, and a handful of other outliers, something peculiar emerges, a whisper of alignment that hints at forces beyond our current understanding. The first clue lies in their shared orbital tilts. Eris's 44-degree inclination and Sedna's 11-degree slant might seem unrelated, but when combined with other extreme trans-Neptunian objects like 2450-236 ATZ and 2199 VP113, a curious pattern emerges. Many of these orbits cluster around specific angles, as if something long ago nudged them into similar orientations. One controversial hypothesis suggests the gravitational fingerprint of a distant, undiscovered planet, often dubbed Planet 9, could be shepherding these objects into shared alignments. Computer simulations show a hypothetical world 10 times Earth's mass, orbiting hundreds of times farther out than Neptune, might explain the odd clustering. But here's the catch: Eris's resonance with Neptune complicates the picture. If Planet 9's influence stretches far enough to tug on Sedna, why hasn't it disrupted Eris's delicate dance with Neptune? Alternative theories abandon the need for hidden planets altogether. Some researchers propose these orbits are fossilized relics of the Sun's birth environment, when passing stars in the crowded stellar nursery yanked Proto-Eris and Proto-Sedna into their strange paths. Others wonder if a close encounter with a rogue planet now long gone could have scattered these objects like billiard balls. The most radical idea involves the galactic tide. the subtle gravitational pull of the Milky Way itself. Just as the Moon's gravity creates Earth's ocean tides, our galaxy's collective mass might slowly torque distant orbits over billions of years. This could explain why Sedna, Eris, and their ilk seem to avoid certain orbital angles as if repelled by an invisible hand. The most tantalizing connection between Eris and Sedna isn't just their paths, it's their surfaces. Both show spectral signs of complex organic molecules, with Sedna's reddish hue suggesting even heavier tholin deposits than Eris's. This raises a provocative question. Could these worlds share more than just odd orbits if their chemistry stems from similar formation conditions? Perhaps in a now-vanished region of the early solar system, rich in specific ices, it might imply they're survivors of a shattered dynasty, the last remnants of a disrupted population. Sedna's extreme distance means it's barely weathered the sun's radiation compared to Eris, making it a potential time capsule of pristiner material. Yet for all the parallels, contradictions abound. Sedna's orbit is so elongated it ventures into the inner Oort cloud, while Eris remains firmly in the Kuiper Belt's scattered disk. Sedna shows no signs of a moon, whereas Dysnomia's presence around Eris offers critical clues about its history. Most strikingly, Sedna's surface appears far less reflective than Eris's, lacking the methane glare that makes its cousin shine like a cosmic disco ball. If these worlds share an origin story, why do they wear such different faces today? The deeper we look, the more these distant dots seem to sketch a hidden chapter of solar system history, one where gravitational chaos, wandering stars, or even sibling planets now lost to time sculpted their fates. Whether Eris and Sedna are true kin or mere cosmic neighbors shaped by shared turbulence, their stories challenge us to rethink how the solar system's edges came to be. Every new discovery in these icy badlands peels back another layer, revealing not just the secrets of individual worlds, but the invisible threads that might tie them together. Pluto boasts 5 moons and entourage ranging from tiny sticks to the massive Charon, its binary partner. Haumea, another Kuiper Belt heavyweight, has 2 known satellites. Even Makemake, smaller and more distant, sports a single moonlet. Then there's Eris, nearly Pluto's twin in size and mass, with just one lonely companion, Dysnomia. This cosmic imbalance isn't just odd, it's a genuine puzzle that challenges our understanding of how dwarf planet systems form. If collisions and gravitational captures are common in the outer solar system, why hasn't Eris collected more celestial hitchhikers? The answer might lie in Eris's violent past. Most multi-moon systems originate from colossal impacts like the Earth-Theia collision that birthed our moon, or the ancient smash-up that created Pluto's satellite family. These events typically spray debris into orbit, where it coalesces into multiple moons over time. Eris's high density suggests it suffered a similarly catastrophic encounter, yet only Dysnomia remained. One theory proposes that Eris's stronger gravity, thanks to its rock-rich core, could have swiftly reabsorbed any smaller moons. Unlike Pluto, where weak gravity allows moons like Nix and Hydra to persist, Eris might have acted like a cosmic vacuum cleaner, pulling stray debris back to its surface before additional satellites could stabilize. Another possibility, Dysnomia might be a moon eater. Its inclined, elliptical orbit crosses regions where other potential satellites could have once resided. Over billions of years, gravitational interactions could have ejected or crashed smaller companions into Dysnomia itself. We see echoes of this process in Saturn's rings, where shepherd moons like Pandora clear gaps by consuming stray particles. If Dysnomia played a similar role, it could explain Eris's barren lunar neighborhood. Yet the absence of moons raises a tantalizing question. Are we sure Dysnomia is truly alone? Current telescopes struggle to spot objects smaller than a few miles across at Eris's distance. New Horizons' flyby of Pluto revealed 4 tiny moons never seen from Earth, a proof that dwarf planets can hide satellites in plain sight. If Eris harbors undiscovered moonlets, they'd likely orbit close to its glare or camouflaged against the starry backdrop. The upcoming Vera C. Rubin Observatory, with its unprecedented wide-field sensitivity, might finally expose these hidden companions if they exist. The deeper mystery isn't just about numbers, it's about what moon systems reveal about their hosts. Pluto's intricate satellite arrangement suggests a relatively gentle formation, preserving delicate orbital harmonies. Eris's solitary moon hints at a more chaotic history where only the strongest survived. Whether by gravity, collision, or sheer cosmic luck, this imbalance reminds us that even in the frozen reaches of the Kuiper Belt, no two worlds follow the same rules. And somewhere in that asymmetry lies a story we've only begun to read. Pluto's bustling lunar system paints a picture of cosmic abundance, 5 moons locked in intricate orbits, each telling a different chapter of their host's violent past. The largest, Charon, is so massive it turns Pluto into a binary system, their gravitational dance creating a stable center point around which the smaller moons, Styx, Nix, Kerberos, and Hydra wobble like celestial fireflies. This complex arrangement suggests a relatively gentle origin story, a glancing collision early in the solar system's history, spraying debris into orbit that gradually coalesced into multiple satellites. But Eris, Pluto's near twin in size and mass, presents a stark contrast. With only Dysnomia as its companion, it feels less like a bustling planetary system and more like a lone dancer in an empty ballroom. The difference might boil down to the violence of their formative impacts. Pluto's collision appears to have been a sideswiper, a cosmic fender bender that lofted material into orbit without utterly disrupting the system. Eris, on the other hand, might have endured a head-on catastrophe. Its higher density and Dysnomia's wildly inclined orbit hint at a far more violent encounter, one that vaporized most of the ejected debris or sent it careening into space. Imagine the difference between tapping 2 billiard balls together versus smashing one straight into another at full force. The first sends ripples across the table, the second might leave nothing but scattered fragments. Another key factor could be location. Pluto resides in the Kuiper Belt's relatively crowded inner band, where passing objects might nudge loose debris into stable orbits, fostering moon formation. Eris orbits farther out in the scattered disk, a sparsely populated region where gravitational interactions are rare. Without neighboring objects to shepherd stray material into place, any moons besides Dysnomia could have spiraled back to Eris's surface or drifted away entirely. This isolation might explain why Dysnomia alone survived. Eris's stronger gravity, owing to its denser core, could have acted like a cosmic claw, reclaiming smaller satellites before they could stabilize. Then there's the question of timing. Pluto's moons show signs of youthful dynamism. Hydra and Nix tumble chaotically, suggesting they're relative newcomers still settling into their orbits. Dysnomia, by contrast, moves with the lethargy of an ancient relic, its orbit worn smooth by billions of years of gravitational friction. If Eris's moon-forming collision occurred earlier in the solar system's history, there might have been more ambient gas and dust to dampen Dysnomia's motion, leaving it in a stable path while other potential satellites succumb to Eris's pull. The wild card in this cosmic whodunit is Dysnomia itself. Most collision-born moons, like Earth's moon or Charon, orbit close to their parent's equatorial plane. Dysnomia's steeply inclined path suggests it either formed under extraordinary conditions or wasn't born from Eris at all. Some models propose it could be a captured object, a stray Kuiper Belt denizen that wandered too close and was snared by Eris's gravity. Yet its composition, as far as we can discern, mirrors Eris's surface a little too closely for a random interloper. Unless Eris somehow skinned Dysnomia during capture, stripping its outer layers to leave only material chemically similar to its own, this theory struggles to hold water. Perhaps the most tantalizing clue lies in what we don't see. When New Horizons flew past Pluto, it revealed a system far richer than Earth-based telescopes had hinted: tiny moons, faint rings, and atmospheric hazes that defied prediction. Eris, still waiting for its close-up, might harbor similar surprises. Current instruments could easily miss small, dark moons nestled close to its glare. Or Dysnomia might once have had siblings that collided over eons, leaving behind ghostly rings or debris fields too faint to detect from Earth. The dichotomy between these two dwarf planets reminds us that no two collisions and no two moon systems are ever alike. Where Pluto's impact left a bustling celestial family, Eris's might have been a solitary strike, forging one enduring bond amidst the chaos. Whether by violence, isolation, or sheer cosmic luck, these distant worlds teach us that even in the frozen reaches of the solar system, history writes itself in unpredictable ways, one impact, one moon, one mystery at a time. Among the countless frozen worlds drifting through the Kuiper Belt, Eris stands out not just for its brightness but for its elusive color palette. Over years of observations, astronomers have noticed something peculiar. This distant dwarf planet doesn't reflect light with the same consistency as its neighbors. While Pluto maintains a steady reddish-brown hue and makes snowy surface shines with unwavering purity, Eris flickers between subtle shades of white and pale pink, as if someone were slowly adjusting a cosmic dimmer switch. These shifts might seem minor at first glance, but in the unchanging depths of the outer solar system, even slight color variations signal hidden drama beneath the ice. The most compelling evidence comes from Hubble's ultraviolet and visible light sensors, which caught Eris transitioning between a stark, almost bluish-white and a warmer, pinkish tint over just a few Earth years. On a world where seasons last centuries and surface temperatures barely budge, such rapid changes defy expectations. One leading theory points to Eris's methane ice, not as a static blanket, but as an active participant in a slow-motion chemical ballet. When cosmic rays and solar radiation bombard methane molecules, they break apart and recombine into complex organic compounds called tholins, which range in color from rusty red to tar black. On Pluto, these tholins accumulate over eons, staining entire regions like coffee spilled on snow. But Eris's higher reflectivity suggests its surface might be cycling through a different process, perhaps fresh methane frost periodically burying these dark compounds, only for radiation to expose them anew. Another piece of the puzzle lies in Eris's elliptical orbit. As it swings from 38 to 97 astronomical units from the Sun, the intensity of solar radiation hitting its surface varies by nearly sevenfold. At its closest approach, last reached in 1896, the faint warmth might have been enough to trigger sublimation along Eris's equator, exposing darker layers beneath. As it retreated, these volatiles could have refrozen near the poles, creating bright caps that gradually spread back toward the midsection. This slow-motion redistribution would explain not just the color shifts, but also the brightness fluctuations that have confounded astronomers for decades. Yet there's a catch: Eris's color changes don't neatly sync with its orbital position. Some darkening events occur when the dwarf planet should be coldest, while brightening sometimes happens unpredictably. This has led to alternative explanations, like cryovolcanic plumes spewing fresh ice across localized areas. When New Horizons visited Pluto, it discovered cryovolcanoes taller than Mount Everest, proof that even distant, frozen worlds can harbor geologic activity. If Eris's rock-rich core generates enough internal heat, similar eruptions might be coating its surface in irregular patches, creating a quilt of contrasting tones that evolve as new material erupts and old layers darken under radiation. The wild card, Eris's mysterious dark spot, that incongruous blemish marring its otherwise gleaming facade. Spectroscopic analysis suggests it might be rich in the same tholins that color Pluto's plains, but with a twist. Its spectral signature shifts over time, as if the chemistry itself is evolving. Some researchers propose this spot could be a cold trap, where heavier gases like ethane condense into a tar-like sludge that darkens when warm and brightens when cold. Others wonder if it's a window into Eris's interior, a place where geologically recent upwellings of organic-rich material breach the surface, reacting unpredictably with sunlight over decadal timescales. What makes these color variations so fascinating isn't just their existence, it's what they imply about Eris's dynamism. Most objects in the Kuiper Belt are effectively frozen in time, their surfaces unaltered for billions of years. Yet here's Eris, subtly shifting its hue like a chameleon adapting to unseen stimuli. Whether through volatile migration, radiation chemistry, or hidden geology, this distant world is proving that even in the solar system's darkest reaches, change is the only constant, and every shift in color is a cryptic message waiting to be decoded. Eris's wild orbital swings don't just tweak its distance from the Sun, they unleash some of the most extreme seasonal shifts in the solar system. Imagine a world where summer means a feeble sun barely warming the surface to negative 380 degrees Fahrenheit, while winter plunges into near absolute zero darkness for centuries. These aren't gentle transitions, they're cosmic whiplash, swinging between extremes that should turn Eris into a static, unchanging ice ball. Yet against all odds, its surface flickers with color variations that suggest something or someone is stirring beneath the ice. The math seems straightforward. When Eris nears perihelion, its closest approach to the Sun every 558 years, sunlight intensifies enough to sublimate trace amounts of methane or nitrogen ice. These gases might briefly haze above the surface before refreezing into fresh frost at the poles, creating bright caps that gradually spread. As the dwarf planet retreats, temperatures plummet, locking these volatiles in place until the next warm cycle. This dance should create predictable, repeating patterns, except Eris's color changes don't follow the script. Observations show its hues shift erratically, sometimes brightening during what should be deep winter or darkening unexpectedly at perihelion. It's as if the seasons are flipping a switch, but the wiring behind the walls is utterly scrambled. One theory blames Eris's tilted axis, a feature we can't yet measure directly. If its poles point sunward for extended periods, like Uranus rolling around the Sun on its side, one hemisphere might stockpile bright frost while the other darkens under relentless cosmic rays. But even this can't explain the localized patches of color change, some no larger than a few hundred miles across. These micro-seasons behave more like weather systems, pockets of activity in an otherwise frozen world. The real enigma lies in the chemistry. On Pluto, seasonal shifts involve nitrogen glaciers creeping across the surface over millennia. Eris's surface is too cold for nitrogen to flow, and its scant atmosphere can't transport ices like Pluto's winds do. Yet something is clearly redistributing material, and at speeds that defy models. Some researchers speculate that Eris's methane might be acting in ways we've never seen. Under certain conditions, methane ice can form a porous, low-density structure called a clathrate, which traps other gases like carbon monoxide or nitrogen in cage-like molecular structures. When warmed slightly, these clathrates can collapse explosively, spraying fresh ice across the surface in geyser-like plumes. If Eris's surface is riddled with these icy landmines, even the faintest solar nudge could trigger unpredictable resurfacing events. Then there's the wild card, time delays. Eris's thermal inertia, the lag between absorbing sunlight and responding to it, could stretch seasonal effects over decades. A dark patch formed in 1896 might only now be reaching its peak reflectance, while changes initiated today might not manifest until 2200. This would make Eris's surface a palimpsest of overlapping climate records, with each layer telling a story from a different century. Untangling that mess would require observations spanning centuries, something no telescope can yet provide. What's clear is that Eris's seasons don't play by the rules. Whether through exotic chemistry, hidden geology, or forces we haven't imagined, this dwarf planet refuses to be a passive ice sculpture. It's a world in flux, scribbling its secrets in colors we're only beginning to decode, and every flicker of its surface is a reminder. Even in the solar system's farthest reaches, change is the only constant. From its bizarrely tilted orbit to its impossibly reflective surface, Eris has spent nearly 2 decades rewriting the rulebook for what we thought dwarf planets could be. Let's recap the 25 biggest mysteries that make this distant world such a cosmic enigma. Why does Eris dance around the Sun at a steep 44-degree angle when most solar system objects orbit in a near-flat plane? What flung it onto this chaotic path? Was it a rogue planet, a catastrophic collision, or something we haven't even imagined? Then there's that mirror-like sheen, bouncing back 96% of sunlight despite billions of years of radiation that should have darkened its surface. Is it freshly resurfaced by cryovolcanoes, or does some exotic chemistry keep its methane ice unnaturally pristine? Don't forget the flickering brightness, those unexplained surges and dips that suggest hidden geysers, atmospheric whispers, or even phase-shifting ices defying known physics. And what about the great size debate? Is Eris actually smaller than Pluto yet denser, or are our measurements still missing something fundamental? Then there's Dysnomia, its lone moon with a dark, charcoal-like surface and an orbit so tilted it defies easy explanation. Is this moon a captured stranger or the shattered remnant of an ancient impact? And why does Eris, unlike Pluto, seem to have no atmosphere at all? Or does it hide fleeting hazes that vanish before our telescopes can catch them? The puzzles only deepen when we zoom in. Those thermal anomalies hinting at hidden heat sources beneath the ice, the dark spot that shouldn't exist on such a reflective world. The sluggish rotation, out of sync with other Kuiper Belt objects, the peculiar way it maintains a gravitational resonance with Neptune despite its wild orbital tilt. Even its color seems to shift over time, as if the planet itself can't decide what shade to wear. And lurking behind all this, the haunting possibility that Eris isn't just another icy rock, but a messenger from the solar system's most chaotic era, a time when planets roamed like nomads before settling into their current orbits. Here's the kicker: every mystery we've uncovered about Eris challenges some core assumption about how the outer solar system works. Its existence forced us to redefine what a planet even is. Its orbit hints at lost giants that once roamed these frozen reaches. Its chemistry suggests processes we've never observed elsewhere, and its sheer refusal to fit our models is a humbling reminder that the cosmos thrives on exceptions. So where do we go from here? The truth is, we're just scratching the surface. Upcoming missions like the Vera C. Rubin Observatory's sky surveys might spot more Eris-like worlds, while next-generation telescopes could finally decode its spectral secrets. One day, a dedicated probe might make the long journey to this icy rebel, peeling back its layers to reveal what really drives these enigmas. Until then, Eris remains a cosmic riddle wrapped in an icy shell, a reminder that some of the solar system's most profound discoveries aren't just about finding answers, but about learning how many questions we've yet to ask. If this deep dive into Eris's mysteries has left you as fascinated as we are, hit that subscribe button and ring the notification bell, because the next big breakthrough in understanding this distant world could drop any day. And who knows, maybe you'll be the one to spot the clue that finally cracks the case. After all, the universe loves a curious mind.